Morning everybody. We are going to do chapter 6.3 part 2 today. Okay, so on Friday you guys had part 1 and today we're going to do part 2. And we're going to start what's called polar notation. Okay, so polar notation, don't know why I wrote that twice, but I did, is going to tell us the magnitude and direction okay, and the way it does that is if we had, let's say, this vector, let's call it vector v, and vector v had a magnitude of 5 and it was at 45 degrees. So we write this in component form as 45 degrees. Okay, or sorry, I meant to put angle. So it'd be 5 angle 45 degrees. Okay, so in component form, in component form it might have looked something like if we had this point out. So component form, this would be at 5, 5. Okay. In polar form, we would actually need to know this magnitude and this angle. So component form, okay, gives us the end of our vector so that we can actually draw it and see its direction and identify its magnitude. Where polar form gives us magnitude and angle. So it's our magnitude of our vector, and if you remember the two lines mean magnitude, and then our angle or theta. Okay, we're going to go from vector or component form to polar form and vice versa. You won't see all of this on your assignment. I cut out quite a bit, but you just so you're aware of what it is and how it works. Okay, so what we're going to do first is we're going to change this vector 4, 3 into polar notation. So we need to find the magnitude and direction. So I'm going to start by drawing this. So this is at 4, 3. Okay, so I know first off it's in quadrant 1. So that tells me that my angle is going to be between 0 and 90. Okay, I know that this is a distance of 4. This is a distance of 3. So technically, you've got that nice little right triangle right there. So we know the magnitude, and let's call this vector u. So we know the magnitude of vector u is just going to be the square root of 4 squared plus 3 squared. So that's going to be the square root of 16 plus 9, which is the square root of 25, which is just 5. Okay, Pythagorean triple. So we now know the magnitude of our vector is 5. So what we need to now do is find the angle. Well, luckily, it's going to be our reference angle right there, and we know sine, cosine, tangent. You guys said that some will hippie cop, another hippie chip, and I said, well, good for you. It's still one of the only ways I remember that. So, or SOHCAHTOA. So we need to find theta, and luckily we've got a lot of options. I'm just going to go with sine. Sine theta equals opposite over hypotenuse. Theta is going to equal sine inverse of 3/5. And I don't have my calculator. Okay, so grab your calculator. Make sure you are in the right mode, degrees. 3/5. So my theta is 36.9 degrees. So my vector in polar form is 5, 36.9 degrees. Okay, not too bad. Let's look at our next one. So we've got this vector is in -5, 6, so -5, 6, give or take if I draw it right. So first thing I always like to do is go ahead and find my magnitude. I'm going to call this vector v. So the magnitude of my vector v is going to be the square root of -5 squared plus 6 squared. So 25 plus 36. So square root of 61. And that does not simplify. So my magnitude is simply square root 61. Okay, so then sine, cosine, tangent. If you remember the domain restrictions, sine, cosine, tangent. So kind of keep that in mind. So let's say I use, I don't know, for some reason, let's use tangent. Mostly because I don't want to deal with the square root of 61, which is maybe the lamest reason, but we're going to go with it. So tangent of theta equals opposite over adjacent. Theta equals, theta equals tangent inverse of 6 over -5. Okay, and that gives us as -50.1, let's do 50.2 degrees. Okay, so 50.2 degrees negative, so that's down here somewhere, -50.2 degrees. Well, we know that tangent, it's quadrant. So again, the domain restrictions were sine, cosine was 1 and 2, and tangent was 1 and 4. So if I just add 180 degrees, I should get there. So I'm going to take my answer, add 180 degrees, and I'd get theta equals 129.8 degrees, which looks correct. Okay, what if we didn't use tangent? What if we did cosine? Let's say cosine theta equals, okay, cosine is adjacent over hypotenuse, -5 over square root 61. Cosine inverse of -5 over square root 61. So I'm just want to try something. -5 over square root 61. And that gave us 129.8. Okay, so two different ways to do this. If you notice on this one, the tangent, it gave us in quadrant 4, and we needed it to be in quadrant 2. So we added 180 degrees to get our angle. Okay, or you could thought about it as this had a reference angle of 50 degrees, and that would be the same as this reference angle, so I needed to take 50 degrees less of 180. Again, that happened in this quadrant because tangent, when we use the inverse tangent in our calculator, it gives us answers in quadrant 1 and 4. Sine is the same, it's going to give us answers in quadrant 1 and 4. Cosine gives us quadrant 1 and 2. So cosine was actually a little bit of a better identity to use this time because it would give us there. It's a better function. But both of them gave us our correct answer. So our answer is square root 61 angle 129.8 degrees. Okay. Sorry, this is just going to be a longer video. So let's change this to component form. So now what we have is we now have a vector and an angle. So I'm going to draw again. First, it just makes it easier. So I have 40 degrees. Let's say 40 degrees. And then I have this vector with a magnitude of 10. If you think about it, so with component form, really it's just kind of an x coordinate and a y coordinate. It's like a point. So we need to figure out the x and the y to get component form. Well, again, we know sine theta is opposite over a hypotenuse, cosine theta is adjacent over hypotenuse, and tangent theta is opposite over adjacent. Okay, so if we look at this, we have, let's go for x first, adjacent over hypotenuse. So cosine of 40 equals adjacent over hypotenuse. So 10 times cosine 40 equals x. We just times by 10 to get rid of that fraction. Okay, so 10 cosine 40. So our x is 7.66. And then to get our y, we have opposite over hypotenuse, which is sine. So sine theta, sine of 40, we know theta, equals opposite over hypotenuse. So 40, sorry, that's a 10. 10 times sine 40 equals y. 10 times sine 40. So 6.43. So my vector form is 7.66, 6.43. Okay. So that was actually not too bad. And most of you will actually kind of start seeing this little pattern. But let's look at our next one. So we have 150 degrees. So 100, so 90, about maybe here. That is such a straight line. So here's 150 degrees, and this has a vector of, or a magnitude of 5. Okay, so then let's look at this. This would be our reference angle, and we know this would be 30 degrees. Okay, because that would give us 180. Here's our x, here's our y. So what if we did, just like what we did on the last one, so cosine x equals, and x we know is 30, so cosine 30 equals adjacent over hypotenuse. So 5 times cosine 30 equals x. And we'd also have sine of 30 equals y over 5. So 5 times sine of 30. So let's see what that gives us. 5 times cosine 30 equals 4.33. 5 times sine of 30 equals 2.5. Okay, so those are my vectors. But this is really cool about these, is we just drew it, found the reference angle, and it worked out really cool. This one, we drew the reference angle. It actually ended up being the same angle because it's in quadrant 1. Well, what if I didn't want to draw this reference angle? And I don't want to, I don't want to draw this. I don't want to find the reference angle. Well, this is actually really cool. If I did So right here, my 5 times cosine 30, instead of doing 30, if I did my original 150, 5 times cosine 150 equals my x, and 5 times sine of 150 equals y, it actually still works out. So if I did 5 times cosine of 150, we get our, technically it's negative. And what did I do wrong? Well, x should be negative because we're going negative direction, and all students cosine should be negative. Okay, when we put it in our calculator with the 150, x gave us negative 4.33, so I didn't have to worry about that or make that silly goof. 5 times sine of 150, oops, that is not right, 5 times sine 150 gave us our 2.5. So they came up with this handy dandy formula saying if we have the magnitude times the cosine of the theta, will give us x, so this is our x, and the magnitude times sine of theta will give us our y. Okay, so we can change anything from polar form to component form using this wonderful formula. I honestly have never memorized this because after I do it once and I could see what's happening, it just makes it a little bit easier. The formula comes in handy if you don't want to always draw your reference angle or draw your triangle and get your reference angle. I still like this because it's one less formula to memorize. The only thing is I tend to forget this, is checking my positive and negatives, but you should be fine as long as you take a second and reflect on where your vector is located. Okay, on the next video I'm just going to do a few application problems, so word problems like you'll have on your assignment.